Alright, we're starting the exponential function review. First section, we are going to fill in all this information given each equation. Parent function on these exponential functions are the base down here. This is the base, and that's the exponent. So we take the base raised to the x power. That's the parent function. Every time we go through a year, second, day, whatever this is, your value is going to be 5 times as much as it was. The asymptote, that's that line it approaches but never touches, is going to be this number outside. It's raised up to, so it raises the asymptote up to. How it's transformed? Well, let's just start with this 2 on the end we've already talked about. It means it's shifting up 2, shifting up 2. And this inside with my x, that tells me it is shifted right 3. On the x, the left and right movements are opposite. Shifted right 3. Oh, I wonder if... Oh, this is the asymptote for the parent function, so that would actually be y equals 0. The new asymptote would be y equals 2. My domain for these, always all real numbers. And my new range, let's go ahead and graph this real quick. So this will be 2. That's my asymptote. It's raising. Hold on, let me pause this first. And this will come up something like, it's going to look something like this. And my new range means it's going to be everything above this line. So that means my range will go from 2 to infinity. And I have to make sure I get the right brackets. These brackets mean they are not equal. These brackets mean they are equal. So it can't be 2 because it's an asymptote. It can't be infinity. So we have to use the curved braces for each of these. Alright. If you want to go ahead and look at this in the calculator would simply just type in 5 and then this key up here, the little house key. You can't see. That key right there. And then we do x minus 3. You have to go to the right to make sure you get out of the exponent. And do plus 2. And then I go to graph. You can see right there that's an asymptote of 2. And then it turns up. The reason it's shifted over like that, that's that shift over. I guess I should have drawn this a little better. It's shifted over. If we got rid of that, let's go ahead and, well, let's not do that. So we can also look at the table. The table has my values over here. You can see that 3 shifted over to the 3. Alright, so next one, number 2. There's negative 3, 2 to the x plus 3. Parent function is going to be my base. My base is what's in parentheses here. 2 to the x, y equals 2 to the x. My asymptote for my parent function is always y equals 0. How it's transformed? Well, this negative 3 in the front, the negative 3 in the front is stretched, vertically stretched by 3, and it is reflected across the x-axis. Reflected across the x-axis. My new asymptote has not changed, so it's 0. My domain for all these are all real numbers, and let's see what this looks like. So my asymptote is still going to be at 0. There's my asymptote. If you want to go ahead and plug in the calculator, make sure we're doing this right. Clear that off. Negative 3 2 to the x plus 3. Go ahead and look at the graph, and since it is reflected across the x-axis, we're actually on the bottom side here. We're actually on the bottom over here. So it's going to look something like that, which, again, not the best graph, but oh well. So my range, since it's coming down, since my range is coming down, it's going to be negative infinity to 0, which is my asymptote here. And these are going to be non-inclusive because it's infinity and an asymptote. Last one up here. 0.8 to negative x minus 3. Parent function will be 0.8 to the x. You can put that in parentheses if you want. My asymptote for my parent is y equals 0. How it's transformed, this negative x in the x value, that is going to be a reflection across the y, and negative 3 is a shift down 3. My new asymptote is at y equals negative 3. Domain for these is always all real numbers. And my new range, it's going to still be the same. Let's look at it on the calculator to see what it looks like. 0.8 to the negative x off minus 3. And look at the graph, and here it is. It is growing like that. It's actually, so it's going to look like this. So that new range is negative 3 to infinity. And since it's non-inclusive, we use the curved braces. Alright, so the next ones, we are going to write each transform function and determine its domain and range. Alright, the function here is vertically stretched by a factor of 4. So let's go ahead and just start writing. Hopefully it works out. And vertically stretched by a factor of 4, that means a 4 is going to go in front of my 0.7 to the x. Reflected across the x-axis up and down, so that's outside, so that's a negative. And translated 3 to the left, that is up at top. Left is positive, so plus 3. My domain are numbers. My range, it's reflected across here, so it's negative infinity to 0, non-inclusive. Next one, the function given here is vertically, and by the way, these are the parent functions, is vertically compressed in the front, 1/2, base is 2, reflected across the y-axis, that's up here, so it's going to be a negative x up here, and translated 3 units down. Plus, this is going to be minus 3 there. My domain are real numbers. My range, what's this negative going to do up there? It shouldn't actually do anything, if I'm thinking correctly. So let's plug it in and see what happens. We have alpha y equals, we have 1, 2, parentheses, 2 to the negative x, minus 3. Look at the graph. There we go. Now I'll flip this that way. Alright, so my range will be negative infinity to 0 up there. Oh wait, oh, I did not put that in close to being right. Hold on. 0.5 parentheses 2 to the negative x minus 3. Let's try that now. There we go. Okay, that makes more sense. So my range is actually my negative 3 to positive infinity. Number 6. The function right here is translated 2 units to the right. So that's up here, 2 units to the right, minus up there, and reflected both across the x and y, so that needs to be negative, and that needs to be negative. So we have f of x is equal to negative 1/3 to the negative x minus 2. Domain is all real numbers. Range, let's go ahead and plug that in so we don't get confused which way everything's going. So we have our negative parentheses 1 divided by 2, and we're raising that to the negative x minus 2. Let's go ahead and look at that graph. The range is going to be negative infinity to 0. That. Alright, bottom. Let's go ahead and solve some equations. Let's go ahead and solve some equations. First one should be fairly straightforward. We have the same bases on both sides. We have the same bases on both sides, so I kind of just get rid of them. 3x minus 3 equals 7x plus 1. Solve for x. I like getting rid of the smallest x first, so I'm going to subtract 3x, subtract 3x. Negative 3 is equal to 4x plus 1. Subtract the 1 here, subtract the 1 there. Negative 4 is equal to 4x. Makes it nice and simple. 4 divided by 4. So I have negative 1 equals x. Okay. So I'm assuming that my base for this is going to be 3. So I'm just going to play with the calculator real quick. So let's start multiplying by 3 and see what happens. 3 times 3 times 3 is 9 times 3. So that's 3 3's, we get 27. Times 3, 4 is 81. Times 3, so that's 5. 3 to the 5th is 243. Let's check it. 3 to the 5th, 243. So I'm going to change this to 3 to the 5th, while this is still 3 to the negative 4x minus 3. Since I have the same bases, negative 4x minus 3 equals 5. And I can just go ahead and quickly solve that. 1x only, so I just go ahead and start getting rid of those. 3, 3, negative 4x equals 8. Divide by negative 4. X equals negative 2. Last one on this page. We have to get a single base on the left and right side. This right here, we have a power to a power. When we have a power to a power, we multiply those. I keep my 2. When I multiply those, that is 4x. Now I'm multiplying my numbers. That means I'm going to add these. Negative 2 plus 2x. Easiest way to write that is 2x minus 2. You could have written -2 plus 2x. I'd rather write it this way. Common bases, 4x equals 2x minus 2. Remember what I said earlier, I like to get rid of the smaller x first. So minus 2x minus 2x. This is 2x equals -2, x equals -1. 2, I guess. Flip her over, see if we have. No, we do not have more. We have word problems. Lots of word problems. We have alright, data was gathered on the population here. We have, oh, by the way, we have equations up here for us to use. Let's go ahead and use those. Before we use them, let's go ahead and talk about each one. First one right here. The first one's right here. The first ones right here are the same equations. Girl with the red hair. These are the same equations. The only difference is this is assuming it compounds every year. This says it's going to compound. The n represents whether it's going to compound semi-annually, quarterly, monthly, could even be daily, and that would be 365. That's how many days are in a year. The rest of these, the ones with the E, please just realize it is the same equation. It just has different variables. The natural decay also has a negative in there, but we assume that. If it's growth or decay, you kind of assuming positive, negative. So these are actually, these three are all the same. These are basically the same. We just have to figure out which one we use. Anything that's population growth or radioactive decay, anything like that, is going to be with the E. Anything where it's either yearly or it tells you specifically a different compounding period is the first ones. Data was gathered on the population of the U.S. states in millions since 1900. Based on data, the growth could be modeled by the function y equals blah blah blah, where x represents the number of years since 1900. According to this function, was a reasonable prediction of the population in the U.S. in 2003 to the nearest tenth of a million. Show your work. What we're going to do, we're simply going to plug in here. This x is the number of years after 1900. 2003 is 103 years later. So what we're going to do, we started, by the way, that says we started with 80 million people basically. We're going to plug that straight in the calculator. You could put it, you keep the x in there and graph it and look at the table, or you can just go to the calculate part and plug it straight in. If you have multiple questions with the same equation, or if you're looking for different values, use the table. If not, just go straight to the calculate. So we have 80.5514 parentheses 1.01289 to the 103. Press enter. That's 301 million. So 301 tenth would be one decimal place. So if I round that to 3. That's it. 22. The number of bacteria in a colony is growing exponentially. So if it's bacteria, that's the population. That's how many bacteria. We're probably going to use one of the E ones. According to the formula, oh no, why is the population of the colony after X days? After its initial population was recorded, how many days it takes the colony to reach 31,250 bacteria? Show your work. Basically what we're going to do, since we're looking for different values, we're going to go to y equals, plot it in the graph, 50 times 5 to the x, and we are going to look at the table, and we want to know where the colony. to reach 31,000. So we're just going to scroll down 31,250, and that's 4 days. Next one, mold. Growth on a certain bacteria can modify this function, where X number of days the material comes wet, and Y is the number of mold spores in a square centimeter of material. Approximately how many days will it take for the count to reach 19,000? Let's just go ahead and put that in. These are ridiculously easy. So that's 32 to the X. Look at the table. 1920, I come over here, and that is 6. It's going to take 6. 24, suppose you, here we go. I actually have to set the equation up. Suppose $800 invested at 8% annual interest, compounded quarterly, and that's 4 times a year. How much money would you have after 20 years? So because it tells us specifically quarterly, we have to use this equation there. I am going to write this equation again so we make sure we plug it in right. There's my equation. Plug in what we know. A of t is what we're finding. I'm just going to go ahead and call it y. P is what we started off with. That's my principal. That's $800. 1 plus my rate is 0.08. That's 8% as a decimal. My n is quarterly, so that's 4. And after 20 years, I can say we're multiply that by 20. And I'm just going to go into the calculator bit and type all that up. I have 800 times 1 plus, and I'm going to do alpha y equals, and do 0.08 over 4. Close my parentheses, raise it to the 4 times 20. Press enter, and I get 3900. And since it's money, I want 2 decimal places. 3, 5. For a certain strain of bacteria, K is 0.825, and that's the rate. When T is measured in days, how long it will take for 40 bacteria to increase to 1,300. So this is bacteria growth. It's going to be one of those E values. It's telling you here too we're going to use a K. Exponential growth, you could use this one or this one. It still both have K's. If you use this one, it's growth, so you're not going to be able to use the negative. So this is the one we really want. Exponential growth, this is if it's going down. So we have P of T is equal to P E to the K T. Alright. How long will it take 40 bacteria to increase to 1,300? So let's fill in what we know. The starting value is 40 bacteria. E is a number. We can use the calculator for that. K is the rate, 0.825. And T is the variable we're looking for. And I'm going to go ahead and throw over here that we have 1,300. What you can do, one, you could solve this as it is and just solve for the T, but what I would rather you do, plug in the calculator. So we're going to have 40, and E is right here on the division sign, blue division sign. That gives me my E, and then we raise that to the 0.825, and we have the X in there, which is, or the T, which is an X in here. And let's go ahead and look at the table. 13,000. Alright, somewhere right after 7 years. If it's multiple choice, you can just find the one that's close to Just put 7. If you want some sort of exact decimal answer, you can always look at the graph and find that and do all that, but that's going to be a pain. So I will be very happy with just 7. Or 7 days. Last one, if you invested $5,000 in a stock that is compounded continuously, those are the ones with the E, at an average rate of 8% per year, how much money will you have after 12 years? So, continuously compounded, A of T equals P E to the R T. Alright, I started with $5,000. E, because it's compounded continuously, my rate is 0.08, and then it is 12 years. How much am I going to get? So there's no variables in here. Let's go ahead and calculate it. We have 5,000 e to the 0.08 times 12. Press enter. We are going to have 13058.48, 2 decimal places since it's money. It's not bad. Alright, last page. Get all this knocked out. Write each expression in radical form. If I write each expression in radical form, what we're doing is we're taking the bottom number of the fraction, we're placing that on radical in front. So, this is written like that. The top number is the exponent, the bottom number goes out here. 1/2, that's simply this. Should be familiar from the last unit we did. And this one right here, that's still a 2. We don't have to write a 2 out here. Ten into the third. That's it. Just moving that out. Alright, next we are going to go the other way. We're going to go the other way. This would be, this will be 2 to the 1/6. This is 1/2, so let's show this twice. This is 10 to the 1/2, and we're raising that to the third power. When I multiply those, I get 10 to the 3/2. That's what this one is. Third one in this row, we have m to the 1/4. That's what this is, and we're raising it to the third. Multiply those, m to the 3/4. Down below, that is a 28. So inside here we have 2 to the 1/2, 28. When I multiply 1/2 times 28, I get 2 to the 14th. See how these are all exponential? And then the W, that is W to the 1/6 times 7, so I get W to the 7/6. And the first one over here, that's P to the 1/2 to the 5th, which is P to the 5/2. And the last one here, the sequence, write the recursive formula for the sequence. To write the recursive formula, simply take these two and divide them starting with that one. So I'm going to go ahead and do alpha y equals. So I have 1, 5, 6, 2, 5. Oh, press the wrong button. 15625 78125. Enter. 1/5. So I am going to go this way, I'm going to multiply it by 1/5 each time. So my recursive formula A of n is equal to my common ratio, which is 1/5, times the number before it, which is A of n minus 1. That's it. And of course my starting value, if asked A of 0 is equal to 78125. But that is the recursive formula there. Basically you just multiply the next number by 1/5. Oh, can't see that.